Welcome to the first lecture on the algebra of matrices, titled Matrices and Linear Maps. The algebra of matrices finds its origin in an old problem: how to solve a system of linear equations. In particular, how to decide when such a system doesn't meet a single solution. This problem arose early. The method of Gauss elimination was known no later than the 2nd century BCE, at least for systems of a few equations and a few variables, as found in an ancient Chinese text called the 9th chapter of the mathematical art. In time, the idea of computing determinants arose. The idea is found in the work of Takakazu Seki, a mathematician from Japan, in 1683, and in the work of Gottfried Leibniz in Europe in 1684. Many mathematicians started to work with determinants: Cramer, Vandermonde, Bézout, Laplace, Lagrange, and Gauss, among others, all contributed to the evolution of the idea of determinant and their growing importance as tools in various areas of mathematics. Then, simultaneously, Binet and Cauchy in 1812 proved a theorem which bears both their name, where the formula for the multiplication of matrices appear for the first time, though still within the context of determinants. Nonetheless, a major step was taken. The discovery of the matrix multiplication, even if it was not immediately realized, meant that a new algebra was discovered. This realization was made by James Sylvester, who recognized that determinants were built from a more fundamental object, the matrix. The term matrix means womb, and was presumably chosen to mean the objects from which determinants are computed. The key observation was that matrices form an algebra. One can add, scale, and under certain natural conditions, multiply matrices. This opens the possibility to study a new world of algebra. This was a major step, taken around the same time, just a few decades later, after Évariste Galois's foundational work on groups and field extensions. A higher level of abstract thought was emerging in mathematics, and opened one of the paths toward a new world of ideas in the centuries to follow. Cayley joined his friend Sylvester in laying the foundations for the study of matrices. Matrices are essential in the study of many disciplines, many centuries past their discovery. It is a beautiful illustration of the way profound ideas evolve over centuries, motivated by a quest for knowledge which transcends any particular need for application. From ancient times and the study of linear systems, and from Descartes' idea of coordinates in the 17th century, to the algebra of matrices, vector spaces, and linear maps, much mathematical talent was spent to uncover a completely new form of algebra beyond arithmetic. In turn, these discoveries provide a cornerstone for the study of geometry and analysis, graph theory, physics, the quantum world, engineering, computer graphics, statistics, and many more applications. It is an example that actually ideas often precede their applications rather than answer them. In its crudest form, a matrix with entries in a scalar field K is a table of scalars. A matrix with m rows and n columns is called an m by n matrix, and we typically index the entries of a matrix with their row number first and column number second. Technically, a matrix is thus an element of the vector space of functions from the set of integers between 1 and m times the set of integers between 1 and n, to the scalar field K. In particular, we know how to add and scale matrices. We simply carry these operations entry-wise. The vector space of n by n matrices with entries in K is denoted by mat mn of K. It is, in fact, the algebraic structure we place on matrices, which is inherited from the algebraic structure of the space of linear maps, which make matrices important. We can actually compute using matrices. The fundamental observation regarding matrices is that they describe linear maps between finite-dimensional vector spaces. This is best understood by starting with a linear map phi from k to the n to k to the m, where n and m are natural numbers fixed throughout this lecture. If we compute phi applied to an arbitrary n tuple x1 etc. xn, then by linearity, we note that we simply compute the linear combination of the vectors obtained by applying phi to the canonical basis of k to the n, weighed by the scalars x1 etc. xn. As we well know indeed, a linear map is completely defined by its values on some basis. Thus, if we know phi is linear, we only need to recall what it does to a finite set of vectors, namely to a basis. Let us give some notation for the m tuples obtained by applying phi to the canonical basis of k to the n. We choose our indexing with a matrix notation in mind. Now, we see how to express our linear function phi in terms of n vectors, which beg to be organized in a table, with each column corresponding to the image of a canonical basis vector, keeping in mind the ordering. Let us therefore write the matrix whose columns are the images by phi of the canonical basis in the same order as we fixed for our basis. We thus get a matrix with m rows and n columns. Inspired by the formula which computes phi from this data, we introduced a new operation, a multiplication of an m by n matrix with an n tuple, which, we now note, we always wrote as a matrix with n rows and a single column. This operation is very important. Given a matrix A and an n tuple x written as x1 etc. xn, we define A times x as a linear combination of the columns of A with the coefficients x1 etc. to xn. Namely, we compute x1 times the first column of A plus x2 times the second column of A plus etc. plus xn times the nth column of A. Note that all the columns are vectors in k to the m, so indeed this linear combination is well defined and gives us again a vector in k to the m. By construction, when we apply this new multiplication to compute the product of the matrix whose columns are the images of the canonical basis by the linear map phi, with some vector x in k to the n, we exactly compute phi of x, as we saw on the previous slide. This creates a connection between linear maps and matrices. Let us explore this connection more deeply. As we have seen, if phi is a linear map from k to the n to k to the m, then there exists a natural matrix with m rows and n columns, which we now call mat of phi for the matrix of phi, whose columns are the images by phi of the canonical basis. The main point of this matrix is that we can use it and a new multiplication to compute phi for any vectors in Kn. Conversely, let us be given some arbitrary m by n matrix A. Using our newly defined operation between matrices and vectors, we can define a map which to x in k to the n associate A times x, which is now a vector in k to the m, obtained as a linear combination of the columns of A with the coefficients provided by x. This map, which we temporarily denote by T sub A, from k to the n to k to the m, is easily checked to be linear. We now make a simple but crucial observation. First, note that if we multiply a m by n matrix A by the first vector in the canonical basis of k to the n, that is by the vector 1, 0, 0, 0, etc., then our formula gives back the first column of A. Similarly, if we multiply A by the second canonical basis vector, we get the second column of A, and so on and so forth. Now, let us pick phi, a linear map from k to the n to k to the m. We can find its matrix, mat of phi. We can then define the new map T of mat of phi. By construction, as noted in the first bullet point here, this map is simply phi itself. We can, on the other hand, start with the matrix A, then form the linear function T sub A. And since it is indeed linear, we can take the matrix of T sub A. This matrix is computed as follows. We apply T sub A to the first vector of the canonical basis of k to the n. That is, we multiply A by that vector. And thus, as we observed, we get the first column of A. But this is also, by definition, the first column of the matrix of T of A. Thus, the first column of the matrix of T of A is simply the first column of A. We then apply T of A to the second vector in the canonical basis, which gives us the second column of A. But again, by definition, it is also the second column of the matrix of T of A. Thus, the second column of the matrix of T of A is the second column of A. Repeating this again and again, we simply conclude that A is in fact equal to the matrix of T of A. Thus, to a linear map from k to the n to k to the m, we can associate an m by n matrix, and to an m by n matrix we can associate a linear map, in such a way that these two associations are inverse to each other. We thus have proven that there exists a bijection between m by n matrices and the space of all linear maps from k to the n to k to the m. Both the spaces of n by n matrices and the spaces of all linear maps from k to the n to k to the m are vector spaces. And so we want to know if our bijection between them, which we just constructed, is in fact linear. It would then be a linear isomorphism between those two spaces. Thus, let phi and psi both be linear maps from k to the n to k to the m. Rewrite their respective matrices as A and B. If lambda is any scalar, and x is any vector in k to the n, it is then easy to compute lambda phi plus psi of x. And we can easily check that it is indeed obtained as lambda A plus b times x. This is a simple computation. Applying lambda phi plus psi to x means computing lambda ax plus bx. We can do so using the definition of these multiplications and using the columns of A and B. Then, we work within the vector space k to the m and use the usual algebraic properties of a vector space to note that we are simply computing the linear combination of the columns of the matrix lambda A plus b with the coefficient x1 to xn. Note that indeed, by definition of the vector space structure on the space of n by n matrices, the jth column of the matrix lambda A plus b is lambda times the jth column of A plus the jth column of B, for any j between 1 and n. We have thus shown the fundamental result that the map which sends a linear function from k to the n to k to the m to its m by n matrix is a linear map. As it is also a bijection, we have learned that it is in fact a linear isomorphism. Matrices are relevant because they are a mean to write all linear functions in finite dimension. Of course, the dimension of the space of all linear maps from k to the n to k to the m is n times m, which is also the dimension of the space of m by n matrices. So, we certainly know that these two vector spaces are linearly isomorphic, but we exhibited a particular isomorphism by fixing certain bases of k to the n and k to the m, and, most importantly, by introducing a new operation on matrices and vectors. This operation is crucial for our purpose. But before we study it further, given the importance of the relationship between matrices and linear maps, let us conclude this lecture by giving another way to understand this relationship. We exhibited a basis for the spaces of all linear maps from k to the n to k to the m for any choice of bases on k to the n and k to the m in our 11th lecture on the category of vector spaces about the dimension of spaces of linear functions. Here, we work with the canonical bases on both k to the n and k to the m. What is the relation between these bases for linear functions and the linear isomorphism we have just constructed? In other words, how do the coordinates of a linear map in this particular basis of linear functions relate to its matrix? Let us denote by E1 to En the canonical basis of k to the n, and similarly let us denote by F1 to Fm the canonical basis of k to the m. We first recall how to make a basis of the space of linear maps from k to the n to k to the m. Fix j between 1 and n, and k between 1 and m. We set xi j k to be the unique linear map which sends ej to fk, and all other vectors e1 to en except ej to 0. Indeed, the set of elements chi jk for j ranging from 1 to n and k ranging from 1 to m is a basis for the space of linear maps from k to the n to k to the m. To get a precise idea on how these bases behave, let x be an n-tuple of scalars which we denote by x1 etc. to xn. Let j be between 1 and n, and k between 1 and m. The image of x by chi jk is the m-tuple which is 0 for all coordinates except for the kth coordinate which is x sub j. If phi is a linear map from k to the n to k to the m, then it is a unique linear combination of the vectors in this basis chi jk. The coefficients of this linear combination are actually exactly the entries of the matrix of phi, if we choose our indices correctly, of course. This is easily checked to be an equivalence. For instance, if we compute phi of E sub j, then we see that we get by definition of xi jk the vector consisting of the coordinates of the image of ej by phi in the canonical basis in k to the m. But this is also by definition the jth column of the matrix of phi. This is valid for any j between 1 and n. Therefore, in an abstract sense, matrices are coordinates for linear maps. However, by looking at them as a table, or maybe even better, as a family of n vectors of k to the m, we can define an operation between matrices and vectors in such a way that we can compute the image of any vector for a given linear map directly from its matrix. This is a core idea of the algebra of matrices. In our next lecture, we will extend our notion of multiplication of a matrix by a vector to a multiplication between matrices of the right size. This operation will be a reflection of the additional operation we have between linear maps, namely composition. We will also see that we know a lot about the algebra of matrices thanks to our efforts about linear maps and vector spaces in finite dimension.